Hi guys, let's do find largest value in each tree row. So we're given the root of a binary tree and they want us to return an array of the largest value in each row of the tree, 0 indexed. So if we take a look at the examples, in example 1 we're given this tree and we would output 1, 3, 9 because basically we check each row for the largest value, and in this one it's 1, in this one it's 3, and in this one it's 9, as we can see here. So we add each of those to a list and return that list. And then in example 2, we're given this tree and we would output 1, 3 because in each row, like the first row, 1 is the greatest value. In the second row, 3 is the greatest value. So we would return a list of those values. So basically in our algorithm, we're going to be going through each row, like row by row in the tree, and add each row into a queue and just have like an updated max value as we loop through to check the which value of which node in that row is the greatest, if that makes sense. So maybe originally our queue is empty and we also need a list. So let's say list is empty, and then we have our max, which we will of course do integer out min value. And then so in our first row, so originally we will add the root of the tree into the queue, right? So we'll add 1 and then into our queue, and then of course in this row then 1 is the max, so then the list will just have 1. In the second row then we'll add 3 and 2, and then we'll loop through each of the values in the queue. 3 is the greatest, so we'll add 3. And then when we get to the third row, we'll have 5, 3, 9. And then we'll check which number in this row has the greatest value, which would be 9. So we'll add 9, and that's what we'll return, is this resulting list. So let's get to the actual coding part, and then I'll explain it as I go too, so hopefully it'll make more sense. But to start, we want to check our base case, which is if the root is null, so we have an empty tree, then we're going to want to just return an empty list because there won't be any maximums. So if root is null, just return empty list like that. Okay, and then if not, so we actually have values here, then we're going to need to initialize our list for our output, and then our queue for our BFS. Yeah, okay. And then we're gonna want to add our root, add root into our queue so that we start out. So let me show you what this looks like as we go. So currently we don't have our max yet, so just ignore this part, but currently we have this, right? Based on what we have so far, we've added the root. So now we can loop through each level. So while queue is not empty, then we're going to be looping through each level at a time. So we're going to want to keep track of how many nodes we have in our queue at one time. So we're going to say nodes in current level is the size of our queue. Because since this is always shifting, we need to store it at the beginning so that we don't end up looping forever as we add new nodes in, or looping the wrong number of times or whatever. So now we need to initialize our maximum. So we'll do this at the beginning so that we always have access to this variable, but that we'll update it within the for loop of each row. While we traverse each row, we'll update it and then we'll reset it for the next row. So that's why we do it out here. Okay, so now we're going to loop through each row. So now we do actually have this because it's right here. Okay. Then we are going to remove the top or the first node in the queue. So this will be 1 to start with, and then this will be empty. And then we will also update our maximum to the most recent max, the current max, or the node's value that we're currently at. So since this is min value, of course this is just going to update to the the value, which is 1. And then after we get our maximum, then we are going to add the node's children into our queue. So if node.left is not null, then we will add node.left into our queue, and then same thing for node.right. Okay, so now once we do this part, because we're at 1, remember, we will add 3 and 2 into our queue. So now our queue will look like that. And let me move this down so we can still see as I'm like doing stuff, because this is like a little bit high up. So let's add this like right here so we can actually see. Okay, and then so once we've done that, then at the end here, after we're done looping through this level, then that's when we're going to want to add our maximum into our list, because we don't want to do that until we're for sure that that's the maximum for this certain row. Like for the first one, it doesn't really matter because there's only one node, but like for this one, we want to make sure we've checked both of these before we actually have the max to add to our list. So then we're going to add 1 because that was our maximum for the first row. Okay. And then at the end here, once we've done this for every single row or level in the tree, then we're going to return our list. But let's still walk through the rest of this just to see what would happen before I run it. So that's the first row, and then the second row, then we've added 3 and 2. So now we are back up here. So nodes in current level is going to be 2. Max is reset to min value. And then, so that's not accurate. Min value, let's just say that. Then node is the top node, which is 3, and then we also remove it. Then if node.left is not null, we're going to add that, so it's not, so we're adding 5. Node.right is not null, so we're going to add that, which is 3. And then we will loop through again. So our next iteration, our maximum got updated to 3. Because our current node's value is 3, which is greater than min value. So that also happened. Sorry about that. Okay, and then our next iteration where I is 1, then we would remove the top node, which is 2 now, and then maximum is the max between our current max, which is 3, and our node's value, which is 2. So we just keep it as 3 because 3 is greater than 2. If node.left is not null, it is null, so we don't do anything. If node.right is not null, then we add that, and it's not null, so we would add that, which is 9. So now our queue looks like this, and then we are done with the for loop now because we've iterated through twice, which is the number of nodes we had in that level. And that's why we need to store this, right? Because now we have 4 nodes in here, but obviously when we started, we only had 2 in this level. So like that would just like screw up the algorithm if we didn't store it in here. But anyway, so we looped through twice now, so we're done. And then we would add the max into the list, and our max was 3. So we're gonna add 3 into the list. Okay, and then we're done with this level, so we are back up here. So nodes in current level is, we removed 2. I don't know what is up with me today, guys. I'm sorry about that. So we have 3 nodes in here. And then we are going to update this to 3 because we have 3 nodes in this level and 3 nodes in the queue, right? Same thing. Max is updated back to min value. And then we are looping through here 3 times because we have 3 nodes. So our top node is going to be now 5, which we removed from the queue. And then max is updated between our current max, which is min value, and 5. So this gets updated to 5. If node.left is not null, it is null, so we don't do anything. And then we don't do anything for right either because that's also null. So that is that for this one. And then now I is 1. We're back up here. We would remove the top node, which is 3. So now we have this. Max is the max between our current max and our current node's value, which is 3, but 5 is greater than 3, so we just leave it. And then node.left is null, so we don't do anything. Node.right is null, so we don't do anything here. And then we're done with this iteration. So then now I is 2. And we update this value to 9 because that's the top node, and we also remove this from the queue. Max is, so we take the max between 5 and 9, which is 9, so this gets updated to 9. Node.left is null, so we don't do anything. Node.right is null, so we don't do anything. And then we're done with our loop because we've iterated through 3 times now. And then we would add our max to the list, which our max was 9. So we're going to add 9 to the list, like that. And then now our queue is empty, so we exit this loop. And then we just get to the bottom where we return the list, which is this. So let's check that and see if that's right. Okay. And then our, oopsie, time complexity is O of n, where n is the number of nodes in the tree. And that is because if we think about the algorithm, right, we need to, like, it doesn't matter what we're doing, DFS or BFS, we have to visit every single node exactly one time. So that is O of n. And then if we look at the algorithm, then like we have this while loop here. So where we're adding everything to the queue and then we're visiting each node in the queue and removing it exactly once. So, and this for loop like gets like amortized, I think, where it's like, cause we're not visiting or like, cause we're only adding one level at a time and then visiting each node in each level one time. So like it still ends up being O of n combined. And then the space complexity is, so you could say it either O of w, where w is the width of the tree, or O of n, where n is the number of nodes in the tree. And I explained this last time, but basically it's because this is like proportionate to the number of nodes in the bottom of the tree, because that would be the maximum number of nodes stored in our queue at one time. But technically, like if it's a complete tree like this, then our maximum possibility of, or I guess this isn't a complete tree because there's no node here, but like the maximum number of nodes we could have in the bottom level is n over 2, which gets simplified to O of n. So technically, like either of these are accurate. And then, yeah, so that's basically it. And then the list, like we don't even store as many as the queue. So, because it's just like one from each level. So that doesn't really matter in the grand scheme of things compared to the queue. So yeah, that's it for this problem. Thank you guys for watching. Sorry if like my explanation was kind of all over the place today.